So we have the equation 3m plus 2 equals 14. Usually when I'm working with students, I don't start with the abstract, but for the video, I will start with the abstract. So to solve, of course, we're going to use inverse operations. We can either subtract 2 from both sides or divide everything by 3. Dividing everything by 3 would mean that I deal with fractions from the very beginning. I'm going to avoid that. So I'm going to begin by removing this plus 2. To do that, I will subtract 2 from both sides. We know that 2 minus 2 would be 0. That's their inverse operations, leaving me with 3m is equal to 12. From here, anytime I have a number and a variable next to each other, I understand that this represents multiplication. So the inverse operation, of course, would be division. And properties of equality say whatever we do to one side, we must do to the other. Well, 3 divided by 3 is 1. And 1m is m. 12 divided by 3 is 4. So that means that m must be 4. I'd like to check my work, so I'm going to go back and substitute. Right, instead of m, I'm going to make that a 4. So 3 times 4 plus 2 is supposed to be equal to 14. Because that's the equation that we were given. Well, 3 times 4 is 12. And 12 plus 2 does equal 14. So I can see that my solution is correct. Okay. I could also solve it using this balance and some algebra tiles. Now, in this case, our algebra tile has an x instead of an m. On the left side of my equation, I have 3 m's. In this case, I'm going to use 3 x's. So there's 1, 2, and 3. There's my 3 x's, and then it says that I have plus 2, so I need 2 positives. Bring these up here. On the right-hand side of my equation, it says that I have 14. Right, so I have these in groups of 5, and 2 groups of 5 equals 10, and then I need 4 more. So there I have a total of 14. That's what I was given, so I need to tell this to be balanced. So we know that equations must always be balanced, right? So my goal is to leave the x's so that I have only one x by itself at the very end. Right now I have 3 x's and 2 1's. I'm going to begin by moving these 2 out of there so that I only have the x's to work with. Well, properties of equality say whatever you do to one side, you must do to the other, right? So right now my equation's balanced. I'm going to grab these 2, move them out of the left side. But if I move them out of the left side, then I must also move them on the right side so that my equation continues to be balanced. So just like we did here, we subtracted 2. Right? From here, now I have 3 x's and I have a total of 12 pieces, just like in our equation. So what I'm going to do is I'm going to split this up into 3 equal groups so that I can know how many ones would have to go into each x. So I can start saying, hey, that one goes to the top one, the middle one, the bottom one, top one, bottom one, middle one, top one, middle one, bottom one, top one, middle one, bottom one. Well, what does that tell me? It tells me that each x must be equivalent to 4, just like our answer, right? So I can double check. I can say if that's true, if I take out 1x, then that needs to be equivalent to taking 4 of these out. There's 1, 2, 3, 4. Okay, and if you notice, it's still balanced. Well, that means if I take, my mouse is playing with me today. If I take 4 of those out, then I should be able to take another 4 out. And yeah, we can see that 1x is equivalent to 4, right? My scale is still balanced, representing that I have the same amount on both sides. A third way in which I can show um, this is in a visual using, you know, manipulatives, things that I can grab, right, that are not virtual. So in this case, I keep talking about a variable as a box or a container that has a certain amount of things inside of them. So this 3M means I have three containers or three boxes, and each one should have the same amount of items in there. That I have two of the counters that are outside of these boxes, and that all together, I'm supposed to have 14 pieces, right? So if we try to connect this to the equation that we solved at the very beginning, in the equation that we saw at the very beginning, we said, hey, let's take off these two. We're going to say, hey, these are outside the boxes. There's two outside the boxes, so I'm not going to count those right now. I'm going to move them out of the way. But hey, if I do that to the left side, I must also do that to the right side, right? So these could be representing the two that are inside those boxes. So that means I have a total of 12 pieces left that are supposed to go inside the boxes, and each box is supposed to have the same amount. Well, in order for me to have 12, I could take 12 counters and do the same thing like what I did in the um, virtual manipulatives, and take 12 of them and split them evenly between all three. So that's 9, right? 3, 6, 9, 10, 11, 12. So right now I have 12. There's 12 there. The two that were on the outside would be those two. So for a total of 14 counters, that means that each box, and again, each box represents n. So one box would have 4 counters in order for me to have 14 altogether.